Hi there, welcome to part 3 in our demonstrational UV-Vis video series. In this installment, I'll discuss how to analyze your measurement data so you can calculate absorbance and mass concentration. I'll also show you examples of overlaid spectra for comparison studies and explain what to look for. Hope you enjoy the video.
So in part 2, we went through how to prepare an analytical or qualitative UV-Vis measurement. Now that we have that data, there are a few things we can do with it. First, we need to correct our absorbance data to take the dilution into account. For example, let's say that to get a peak optical density of about 1, you had taken 1 ml of your sample and diluted it in 99 ml of water. That's a 100-fold dilution. If on the UV-Vis you measured the peak absorbance at 1, you would multiply that by 100, which gives you a dilution-corrected peak absorbance value of 100. You can use Excel to multiply this number on all of your measurement values. We recommend you use the analytical measurement method we described in part 2 in order to calculate the most accurate dilution factor instead of relying on your pipette volumes. Here at nanoComposix, we've put together a spreadsheet that does all the calculating for us and automatically generates charts for every UV-Vis data set that gets entered. We have a simplified template that we would like to share. It's available for download on the website by visiting this webpage. Once you enter the raw data set and input your nanoparticle sample volume and total volume after dilution, the spreadsheet will have everything it needs to generate the UV-Vis spectrum and stats. Here's a chart where we've overlaid spectra from 3 different sizes of silver. These spectra are normalized, which means we took the spectrum from each material and divided the data by the peak absorbance so that all of their peak absorbances are at 1. Normalizing allows us to more easily see shifts in the peak location or wavelength. As you can see, the smaller sizes are closer to the shorter blue wavelengths of light, so we call that blue shifted. The larger sizes are closer to the longer wavelengths of light, so we call that red shifted. Here's what we get if we add in all the sizes in between. You can see a clear progression of the peak absorbance toward the longer wavelengths as the size increases. Now let's undo the normalization and just look at the dilution-corrected data. Here's a chart showing all of those same particles at the same mass concentration of 1 mg per ml. The peaks are still at the same wavelength, but now you can see that as the particles get larger, the optical density goes down. This is because the number of particles per milliliter is different. If we say the concentration is at 1 mg per ml, that refers to the mass of silver. If we take the same masses of silver and cut them into 10 nanometer spheres versus 100 nanometer spheres, there will be way more 10 nanometer spheres. Because there are way more particles, the optical density will be higher. Doing the math on volumes, we would expect the 10 nanometer solution to have 1,000 times more particles than the 100 nanometer solution. But why isn't the optical density 1,000 times higher? It's because optical density also depends on particle size. A 100 nanometer particle is about 250 times more optically dense than a 10 nanometer particle. That's why there's only about a 5 times difference in optical density between the 10 nanometer and 100 nanometer particles. Next, I'll show you some examples of silver nanoparticles that have undergone varying degrees of aggregation. This is a chart that demonstrates a small degree of aggregation. The slight elevation in the baseline in the 450 nanometer to 550 nanometer range is a telltale sign of aggregation because, as I mentioned before, larger sizes of nanoparticles absorb more in the longer wavelength or red region of the spectrum. So as these larger aggregates form, there will also be an increase in absorbance in that range. This in turn typically results in a decrease in absorbance at the peak because some of the nanoparticles that once absorbed at the peak wavelength are now in the form of aggregates. The absorbance at the peak drops and absorbance increases in the wavelength regions that the aggregates absorb. You can see that the absorbance at the peak dropped by about 20% here, and there is now a slight increase in absorbance at the baseline in the 450 nanometer to 550 nanometer range. Here's another example of some silver nanoparticles that have undergone a more severe degree of aggregation. Here you can see that the spectrum of the material has significantly broadened and also has an elevated baseline. The absorbance of the peak wavelength is once again affected as the same principle applies here, whereas the aggregates form, the peak absorbance drops and an increase in absorbance at longer wavelengths appears. Since this case of aggregation is much worse than the previous one, there is a drop in peak absorbance of about 40% instead. In this particular case, the aggregation results in not only a broadening, but also a secondary peak. This occurs when the aggregates that form are of similar size, resulting in a somewhat discrete secondary peak. This is the most extreme case out of the ones I've mentioned, as the drop in absorbance of the main peak is almost 50%. There are also cases where silver nanoparticles will change over time and not necessarily aggregate. In this case, what we see is a slight blue shift in peak wavelength of about 3 nanometers and an overall narrowing of the shape. This is often indicative of a change in the size distribution. Silver nanoparticles in an aqueous dispersion can release silver ions from the surface over time, which cause the nanoparticles suspended to essentially shrink in overall size. As I discussed earlier, smaller nanoparticles will absorb the shorter wavelengths of light, which explains the blue shifting that we see here. The decrease in overall size is verified by TM image analysis of this material to be a decrease of about 3 nanometers. Additionally, as silver ions are released from the surface morphology of the nanoparticles will change as slight imperfections in the facets may become smoother, or the particles can become more spheroidal, which can result in the narrowing of the spectrum, as we see here. In certain conditions, this process also results in an increase in absorbance, because as silver ions are released from the surface, the ionic silver can reduce and self-nucleate to form new particles. This process produces a new population of very small nanoparticles, which, as their numbers grow, drive the absorbance up as well. This phenomenon is confirmed by TM analysis of the material. As you can see, in this TEM image, there is a large population of very small nanoparticles in the 2 to 3 nanometer range. If you're interested in the optical properties of some of our other plasmonic materials, visit our Plasmonics webpage where you can view the absorbance properties of many of our nanomaterials. For example, you'll find that the absorbance properties of some of our materials like silver nanoplates and the gold nanorods are tunable through a wide range of wavelengths, from 550 nanometers to 1150 nanometers. This is because the absorbance properties are size and shape dependent, and as their sizes and shapes are tuned, so are their absorbance properties.
And that concludes part 3 in our UV-Vis series. Thanks for watching. I hope you enjoyed the video and that you found it helpful. Please be sure to leave any comments or questions below, and check out our products, services, and knowledge base on our website at nanoComposix.com for more information. Thanks.